In tutorial 2, we will solve a set of 5 problems on frequency hopping spread spectrum systems. As you can see in the first problem, we are asked to calculate the number of minimum bits required in a PN sequence if we use FHSS, and the channel bandwidth or signal is basically specified as 4 kilohertz, and the spread spectrum bandwidth is 100 kilohertz, which is greater than the channel bandwidth. As we know, the number of hops required in order to spread out this 4K signal over 100K is nothing but the ratio of the spread spectrum bandwidth to the channel bandwidth. So the total number of hops is equal to 25, and in order to realize 25 hops, we require minimum number of bits equal to log to the base 225, because 2 raised to the number of bits in a PN sequence is basically equal to the number of hops over the spread spectrum bandwidth. So we basically calculate the minimum number of bits required as log to the base 2 of this number of hops, which is equal to 4.64, and we round it to the next highest integer, which is equal to 5. Rounding to lower will not do, because 2 raised to 4 is 16, which will not give you the number of hops that is required. In the second problem, we are given a 4-bit PN sequence and asked to find the total number of possible hops, which is basically a reverse procedure to what we did in the first problem. So straight away, if we are given number of bits, then 2 raised to the number of bits in the PN sequence is equal to the total number of hops, which in this case turns out to be 16. And moreover, the bit rate of the PN sequence is specified to be equal to 64 bits per second. So we need to find the number of finished cycles per unit time of this PN sequence, since there are 64 bits in a second and there are 4 bits in a PN sequence. So a total of 64 by 4, 16 cycles of this 4-bit PN sequence will be covered in 1 second. So therefore that settles part 2 of problem 1b. In the next problem, we are given a table of data. To start with, in the first row we have the time index from 0 to 19. Corresponding to every unit time, we are given the input data in the form of a bit stream, as you can see, and we are given the frequency for every time index. So we see that there is a hop from F1 to F21 to F11 and so on and so forth for every such time index, and corresponding to every such hop we have a free PN sequence which is assigned, which comprises of the last row of this table. So the questions, there is a set of questions to be answered, and we see the first one deals with finding the period of this PN sequence in terms of the number of bits of the PN sequence, and a close observation of row number 4 over here, which is nothing but the PN sequence, reveals basically that we have, after every set of 5 such tri-bit PN sequences, we have a repetition. Let me just illustrate that. So we see that we have this first set of PN sequences 001, 110, 011, 001 and 001. We see that this basically repeats after once again, and so on and so forth. So what we notice, this should basically be let me just repeat this once again. So we have this 5, 1 2 3 4 5, and this same thing is repeated over here, as we can see. So this sequence is similar to this, and so on and so forth. So basically what we have is the period of PN sequence, which is in this case is 5 into 3, which is 15 bits. The second part of the question is what form of FSK is this system. So what we notice is that the pattern of frequencies are such that if you are able to map a single frequency dibit or tribit to a corresponding frequency, then we should be able to get this answer. So what we notice is, for example, is that we have F3 frequency, which is assigned to 1 1 over here, rather the other way around. One combination of 1 1 is assigned to F3. Similarly, we notice that a combination of 0 0 is assigned to F0, and we also have once again a combination of 1 1 assigned to F3, and here we can see 1 0 assigned to F2. So we see some kind of a pattern emerging here. So 0 0 is F0, and we see 1 1 has been mapped to F3, 1 0 maps to F2, and presumably 0 1 would map to F1. In fact, we have a 0 1 combination at the beginning itself, which is mapped to F1 and F2 1. So we'll see that F2 1 will subsequently map, or should subsequently map at the receiver to F1. So this is something we will show at the end. But it appears like we have a merry FSK system to start with. That is quite clear, and it also is obvious that per symbol, that is per F, we have a die-bit combination. So we have a number of bits per symbol equal to 2, and we have a set of 4 frequencies, as we can see here. So we have the number of FSK frequencies equal to 4. The length of the PN sequence per hop, we can see that the frequency keeps changing for every time index, and every time index has a length equal to 3. So this is equal to 3, and we also notice that for every signal element, that is every die bit, the frequency changes, and so there are 2 frequencies basically being hopped onto for every die bit combination. So basically it's a case where the number of hops is greater than the number of signal elements. So this is obviously a fast FH system. Since we have 3 bits per PN sequence, so we can have as many as 2 raised to 3, which is equal to 8 carrier frequencies. And finally we need to figure out a way in order to demodulate the frequencies. So the question is how to map these frequencies F21, F22, F10 back to a frequency which belongs to this set, which is nothing but the modulating frequency. So the idea to do that is by choosing the given frequency. For example, we choose F21, and the idea is to map this F21 to one of these. So how to do that is basically by taking this subscript and finding out the subscript mod 4, because it's a 4 FSK system basically. So m is equal to 4. So 21 mod 4 can be calculated in the standard form as to how we find out mod. So we basically just divide 21 by 4. So we know that this is nothing but 1 is the remainder. So this remainder is nothing but the result of this operation, that is 21 mod 4. So we map the subscript 21 to the subscript 1, which is the remainder of this operation. So we map f21 equal to, and that is what I was talking about over here. So this combination of 0 1 is basically f1. So you can try it out with other elements as well. For example, in the case of f11, what we need to do is 11 mod 4. So this, after this calculation, will be equal to 3, and so f11 maps to f3. So this f11 will become f3, which is nothing but the frequency corresponding to the die bit 1 1. So this basically completes this particular problem, and we have the answers over here, which was what was solved for before, and we will always see that the mapping procedure or the demodulating procedure for each of these frequencies will give back a set of frequencies, a frequency corresponding to a set of bits. So that is what we have in this table, which is nothing but the demodulated frequency. So we move on to the third problem. In this problem, we are given a PN sequence which is generated using a 20-stage linear feedback shift register, and it's a maximal length sequence. So basically we know that a 20-stage linear feedback shift register will give you a maximal length of 2 raised to 20 minus 1. So that will be the number of states for this shift register. Now each state of the register basically dictates a new center frequency within the hopping bandwidth, and it is further specified that the minimum step size between the center frequencies is 200 Hertz. So basically if I have 20 states, and if each state gives me a unique center frequency, and the gap between center frequencies is 200 Hertz, then the number of states into the number of such center frequencies, and therefore the gap between them, will give me the total hopping bandwidth. So straight away the first part of this problem can be solved as that is the hopping bandwidth basically is 2 raised to 20 minus 1 into the separation between the center frequencies. So this turns out to be 2 raised to 2.1 into 10 to the power of 8. In the second part of the problem, it is asked as to what is the chip rate. So basically this is pretty straightforward. The clock rate of the chip is already specified equal to 2 kilohertz. So the chip rate is nothing but that clock rate, which is the hop rate also. So that is equal to 2000 chips per second. In the third question, it is asked as to how many chips are there in each data symbol. So this is basically nothing but obtained by first finding out how many symbols are there in each second. So in order to calculate that, we make use of the last part of the data provided in the problem. That is, we have a 8 array FSK system, and the data rate is 1.2 kbps. So the data rate divided by the number of symbols. So for a 8 array FSK system, we have 3 bits per symbol. That gives you the symbols per second straight away. And then we find out, we already know that the number of chips per second is 2000. So the number of chips per second divided by the number of symbols per second in this case will give you the number of chips per symbol. So that's nothing but 5. Finally, the processing gain in dB is asked. So we already know what is the hopping bandwidth, which is 2.1 into 10 to the power of 8. So this divided by the raw data rate, which was 1.2 kbps, gives you the processing gain. This is basically the definition of processing gain for FHSS systems. We merely convert it to dBs in order to obtain the final result. In problem number 4, this is an interesting problem. We have a terminal which has to communicate with a satellite. So the distance between the two is denoted here by h, and we further have a jammer that is trying to disrupt this communication. So what we do is that we basically are having a system which is likely to be affected due to the operation of a jammer. So what we first or rather what is asked over here is to compute what is called as the radius of vulnerability. So this is defined as the radius outside which the communicator is unconditionally safe from the jammer. It is to be noted that it is a ground based jammer. So we first take a look at the data which is provided to us. So we are given the frequency hopping rate, which is 10,000 hops per second, and this is of course specifically in order to avoid the threat of what is called repeat back jamming. So every time this signal is sent, as long as the jammer is outside the radius of vulnerability, it will be unable to jam the communication system. So in order to find out that particular radius, what is done is we first calculate the time which is required to complete a hop from the terminal to the satellite. So there are two elements which comprise of this time. One is the duration of the hop, because every hop will occupy a certain time duration, and that is to be calculated basically based on the data that is provided to us. So we have this equal to 10 to the power of 1 divided by 10 to the power of 4 seconds. That is because we have already been specified the hopping rate. So we merely take the ratio of that in order, or rather the reciprocal of that, in order to find the time. We further see that there will be some propagation time involved for the signal or the entire hop in order to propagate from the terminal to the satellite. So the addition of these two times basically gives you the total time that is required for the completed hop. So the t part is due to this completion of the hop which is required, and h by c is nothing but propagation time. C is of course the velocity of light. So there is this jammer R. So what it needs to do first is to try and get this information. So that requires a time of R by C, where R is the distance between the terminal and the jammer, and then the propagation time between the jammer and the satellite receiver where the jamming will actually happen. So that propagation time is nothing but d by c, where d is the distance between the jammer and the satellite. So this communicator will be unconditionally safe from the jammer, provided that the time required for communication between the terminal and the satellite is lesser than the time required for the jammer to obtain the information from the terminal and then jam the signal at the satellite receiver. So that is what is formulated in this expression, t plus h by c lesser than or equal to r by c plus d by c. So now we need to solve this in order to find this r, because we are trying to find the radius of vulnerability, that is this r, the distance between the terminal and the jammer. So we merely just simplify this expression, and we see that r basically turns out to be equal to, so we h plus c into t. We take the equal to sign for the worst case condition, and we see that of course that d is related to h and r as well. Now the solution, the calculation of r requires solution of this equation. However, we can make use of the condition that r, that is the distance between the terminal and the jammer, is much less than h. So in which case we can neglect this r and h cancels out, and we get I'm sorry, so what we do is yeah, right, so we have r equal to this, so r is much lesser than h, so r is neglected, h is cancelled, and we have r equal to c into t. C is already a standard value, and t it's given, or rather it's been already calculated as 10 to the power of -4. So what we have is r equal to 30 kilometers in this case. Now in order to have a more precise relationship between r and the rest of the parameters, we also need to include the fact that apart from obtaining the information from the terminal and then jamming it at the satellite receiver, the jammer also requires some time in order to process the information, in order to exactly determine the hopping sequence. So we denote that time by tau, and as you can see in this expression, r by c plus d by c, we have an additional processing time at the jammer equal to tau. So obviously if this processing time, this processing time is going to be some positive number, and that is going to be beneficial to us, because let's say for example we take tau equal to 10 microseconds and solve the same problem as in part A. What we notice is that the radius of vulnerability reduces to 27 kilometers, which is beneficial to us. And so part B of the problem, the solution is a more precise solution, provided this processing time at the jammer is specified. So this particular problem highlights the calculation of the radius of vulnerability, beyond which the terminal is unconditionally safe from the satellite as far as jamming is concerned. So finally we have a problem that deals with narrowband and wideband jamming. So in this case we are given a FHSS BFSK system, and we have a binary data rate at 20 kbps. The unspread BFSK system has a bandwidth of 25 kilohertz. The received power is minus 15 dBm, and we have a jammer which has a maximum power of minus 20 dBm, and we have two cases. One is this jammer can operate as a narrowband signal with 25 kilohertz bandwidth, or it can also occupy the entire spread signal bandwidth. So that would be a kind of a broadband jammer. So the spreading factor is specified as 25. So straight away we see that 25 kilohertz, that is the unspread bandwidth multiplied by the spreading factor, gives us the total spread bandwidth, which would be 625 kilohertz. Further, we have specified the PSD of the AWGN channel. So this is 10 to the power of minus 11 watt per hertz. The problem to be solved is we need to find the SNR in dB for the narrowband jamming case as well as the wideband jamming case, and we need to see if there is any improvement in this SNR for the narrowband case or compared to the broadband case. So it shall show turnout that the SNR requirement for the wideband jammer is going to be better than that of the narrowband jammer. There is going to be an improvement, so we'll see that. So we'll list out the various parameters. To start with, we had the received power in dBm, so we convert it to watts, and we are also given the bit rate, that is 20 kbps. So based on that, we know the bit duration, which will be 1 by 20 kbps. Based on this data, we find out the bit energy, which will be equal to power into the time, which gives us the bit energy basically at the receiver. The jamming power is specified already as minus 20 dBm, so we convert it to watt. And so we solve the first case, which is a narrowband jammer. So we are given the jamming power Pj, which is 10 to the power of minus 5, which is nothing but minus 20 dBm. And so we also know that it has a bandwidth. The jammer is a bandwidth of 25 kilohertz. So we can find the power spectral density of the jamming power signal basically. And so the SNR in case 1 is equal to bit energy divided by the power spectral density of the jammer plus, of course, the power spectral density of AWGN is already specified. So we calculate the SNR for narrowband jamming, and it turns out to be 5.86. For the wideband jammer, as I previously mentioned, the spreading factor is equal to 25. The unspread bandwidth is equal to 25 kilohertz. So the bandwidth of the jammer signal is equal to spreading factor multiplied by unspread bandwidth, which is 625 kilohertz. So we recalculate the PSD of this wideband jammer now, and so the difference lies here. We have a wider bandwidth, and so the PSD, it turns out, is lesser than the PSD as compared to the narrowband case. And this has a clear-cut impact on the new SNR that we calculate. The AWGN PSD remains the same, but the PSD of the jammer is now reduced, and so the SNR at the receiver has increased. So what we notice is the SNR in case of wideband jamming is greater than that of narrowband jamming. So this is basically because the same jammer power, which is 10 to the power of minus 5, is now spread over a larger bandwidth, which gives you a smaller power spectral density, and that gives you better immunity to jamming. So the SNR at the receiver for wideband jamming is much greater than as compared to the narrowband jammer. The improvement is merely calculated by finding the difference between the two cases, so that turns out to be 11.98 in this case. So this concludes tutorial 2. We solved a set of 5 problems covering certain aspects of FHSS. Thank you.